Okay, last time we talked about the basic ideas of phase space and how you linearize around a fixed point. Now we want to talk about what happens with after we found the solutions, but now we tune in our parameter tau and see how if we change the function slowly, we might arrive at behavior that changes with tau. So let's choose the kind of classic version of this where we have x axis, and let's say that we have a quadratic. A simple quadratic that goes like this. And this one is just barely touching. And then this one is intersecting twice. Okay. So and each of these, how do we get them? Well, we might get them by having different values of tau. So let's make this concrete and say that this is just equal to x squared plus tau. So if tau is a positive number, we're in this case. If tau is equal to 0, we're in this case. And if tau is equal to a negative number, we're equal to this case. Cool. Fixed points. Any fixed points in this one? No, there are none. We just run to bigger and bigger numbers. So there are no fixed points for the case of positive tau. This one, fixed points. Yes, we got two. We got this one, stable. This one, unstable. Great. We can do a local linearization around those. We can find the rate of cascade into it. It's going to be closely related to the derivative of x evaluated near those two fixed points. Yes, we know how to do that. Cool. But this tau is a negative value in order to have the 2 points. And what about this one where we're just barely touching? Well, this direction we come in and we approach, but this direction we run away. So this is called a half stable point, where it is stable on one side, unstable on the other side. Cool. That's almost the whole story. But let's think, rather than thinking about this as a function of time, now that we've mapped out the phase space, let's think about it as a parametric set of steady state solutions that all depend on tau. So we've got two x stars here, we've got one x star there, we've got no x stars here. So if we make a function of our x star, our steady state solutions, as a function of tau, what do we have? Well, let me draw that a little better, because we were particularly interested in the negative values of tau. X star. For positive tau, we have no solutions. For negative tau, we have two solutions, one steady, one unsteady. The unsteady one is at positive x's. The steady one is at negative x's. And they're centered, they're always symmetric, because this is just a simple quadratic right around the center. So I can draw a sideways parabola like this, and I can put that point there. So imagine we start with a negative value of tau. We have the possibility of having an unstable steady solution at positive x, or a stable steady solution at negative x. But if we were to somehow reach into the system and dynamically adjust tau, we would be moving over in this direction. And then we reach this point where we have a half stable. And then if tau increases, there's no longer any more solutions. This is called a blue sky, like it happened out of blue sky, which in this case would be there were no solutions, now there's solutions. Blue sky bifurcation. What does bifurcation mean? Well, in this case, it means you go from one solution to two, zero solutions to two. So, but in other cases that are equally common, you are splitting your solutions into multiple solutions as you change the parameters as it goes along. So it bifurcates. Start out with one solution, it becomes multiple solutions. Bifurcate becomes two. Okay? Let's think of a slightly more interesting example. Let's think of one with a cubic. Okay, so here's a simple cubic polynomial, which also has a tau, an additive tau. But then we've got minus x cubed plus x. So this is the cubic part. Let's think about how that works. Well, for very large x, far away from the origin, the x cubed one is going to dominate. So we know we're going to go towards negative infinity on this side, towards positive infinity on this side. But for very small x, this is going to be small, this is going to be big. So we would have a positive slope right at the origin. So we have something that goes like this. And if you think about it for a little while, you'll notice that it should intersect, if tau were 0, that it should intersect at plus and minus 1 is where those would go through. So we have 3 fixed points. What are they? Well, boop, 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 steady, boop, 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 unsteady, boop, 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 steady. Okay? So we have 3 fixed points, 2 of which are steady, 1 of which is unsteady, with tau equals 0. What happens as we move towards positive tau? Well, we can add up, and one of them is going to be the one that just kisses here, and then we have that one, and so we would have a half stable here, and we'd have a stable there, and then the other one we could go down, we'd have a half stable here, we have a stable here. And then if we go farther up, we just have one solution, which is stable. If we go farther down, we just have one solution over here. Okay, so let's make our steady state plot. How many have we got? Well, we have somewhere between 1 and 3. Let's center ourselves on tau equals 0 again. So here's tau. Here is our fixed points. All right, tau equals 0 is the case where we had plus 1 and minus 1, plus 1 and minus 1, and they were both steady, and then 0 was an unsteady. And if we go over a bit to this direction, towards positive tau, this one is going up a bit. These two are getting closer to each other, unstable, stable, and at a certain point, they hit at stat half stable and disappear. This one continues up. What about going the other direction? Well, there's symmetry. This one goes down like that. And now in this direction, the unstable and the stable branches merge into half stable, but the other direction. So now it's unstable in the bottom, stable in the top. Okay. That's how the fixed points evolve as we change tau. Let's think about it a little bit more dynamically than that. What if we have a tau knob and we start somewhere over here, boop, 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 anywhere over here in terms of our x's? Well, the first thing we do is we fall down into the stable solution, and that would be true if we were up here too. We'd fall into the stable solution if we didn't choose it as our initial conditions. So we might as well assume that we start out on the stable condition. Now we start tweaking tau, and we might be moving this direction, dude. And even though there are these other solutions, we won't tend to jump onto them unless there were like noise in the system or something, because we're already on a steady state solution. And so as long as the noise was modest, we would just ride along on this steady solution until we reach this point. And if we could turn tau a little bit beyond that, we would actually fall off of this branch and collapse onto this new steady state solution. And then we could continue upwards. So there's a step change in our behavior. We switch from one regime of behavior, sitting on one steady state, to a totally different one. And often we might make that change very fast. This is a tipping point. This is what a tipping point is in dynamical systems. This is one example anyway. Okay, well, what if we go up to here and then we turn around and we go back? Now look what's happening. We're going back over the same range of tau that we started out on, but we're riding on a different solution. And we keep doing that until we cross this tipping point, at which point we fall back down to here. So if we were going back and forth in excursions in tau, we would be riding on different solutions on the way up than we're riding on the way down. that kind of dependence, path dependence on where your solution is as you change a parameter is called hysteresis. Hysteresis does not occur in linear systems. It doesn't occur in all nonlinear systems either. But if you find hysteresis, or if you find tipping points, then you know that your system must be linear, even though, because the linear cases just don't have that much interest in them. However, not all nonlinear systems have tipping points, and not all nonlinear systems have hysteresis. So you have to be careful. It's if those things, then nonlinear, but not the other way around.